Okay, so I want to do an example of applying Stokes' theorem. So I picked number 2 in 20.2, just because. So what we have is a vector field F that's given by y minus x and 0. And Chris has already been asking what sadistic asshat switched your y's and your x's around. And I said, someone who wanted the curl to be interesting did that. And C, the curve that I'm trying to, interesting. There's a C in here. C is the boundary of Z is 4 minus x squared minus y squared. What the heck is that thing?
It's downward facing, what's it called, a parabolic ellipse or paraboloid?
Well,
This is a circular paraboloid.
Yeah.
So that would be something like this.
Yep.
So this is the surface. 4 minus x squared minus y squared is Z. Right? So that's my S, right?
4 minus r squared, essentially.
Nice, which is 4 minus r squared, right? And then this thing on the bottom here, right? This is at the xy plane that I've drawn.
Yep.
I cut this thing. Let's see, what did they tell me? Oh, they told me that surface is oriented upwards, right? So that's like, here's a normal vector. Yeah? So then which way does the curve have to, the curve's orientation have to go for me to use Stokes? Yeah, it has to go right-hand rule, right? So that's counterclockwise looking down at it. You guys all with this? And what I want to do is I want to compute, they told me to compute, sorry, I missed a part of the problem. I didn't read the directions. You guys ever do that?
Yes.
Yes. Okay, so they wanted me to compute the line integral around C in 2 different ways. They want me to do it using Stokes and to do it directly. I'm just going to do this using Stokes because I trust that you guys can do line integrals. Cool? So I have this thing that I'm starting with. What should I make that into? Okay, so Stokes has a whole crap load of assumptions, right? So what do you need to check?
So the surface is a piecewise smooth orientable surface with an oriented boundary curve C.
Okay, so I need to make sure that my surface is orientable and smooth. Check, check, right? It's paraboloid.
C is
I need the boundary curve to be closed, simple,
piecewise smooth.
piecewise smooth. Check.
Yep.
Hell yes.
And
I need the vector field to have continuous partials on some kind of fattened up something or other.
Yep.
Where are your vector field's partials continuous? Everywhere. Yes! Right? I don't have to worry about any problems. So I can apply Stokes to this thing. And when I apply Stokes, I get that this should be the integral over the surface, right?
Yep.
Of what?
Curl of F dA. Dot of dA, sorry.
Okay, so far I've just written Stokes down, right? Okay, so I should check and make sure the orientation agrees. Cool. They told me something about the orientation agrees anyway. Okay. Now, what do I do?
Probably want to find the area.
Okay, so you need to calculate 2 things, right? Some of you are suggesting one, some of you are suggesting the other, but whatever. You need to calculate the curl, and you need to calculate a surface integral, right? I'd start with the curl, personally.
Yep.
Then we also need to parameterize the surface.
Yeah, so to compute the surface integral, right, we'll have to parameterize the surface. So I need both a curl computed and a surface parameterized. You guys all good with that? So first things first, I'm going to compute the curl. So what's the curl of F?
I'm doing the calculations right now.
Okay, what
It
was the
looks
trick?
like CYX, ZYX.
Okay, so the z component's 0.
Yep, so 0.
0 minus
Um,
the,
y partial of z, so it ends up being another 0 because it's partial of z.
okay, the y component, and then with respect to z, great, that's going to be 0. And then this guy's going to be, see, so I did z, y, x. So that's going to be the partial of y with respect to
Z.
specifically not y, right?
Yeah.
That's going to be z. And then this guy is,
0. 0 over partial of something.
so that's z, y, x, z. And then this one's going to be the y component. So that's the partial of minus x with respect to something. And then
partial
the
of y.
partial of y with respect to something. And those are what?
With respect to x and with respect to y.
Yeah.
So we end up getting a 0, 0, negative 2.
With respect to x and with respect to y. So I found out my curl is 0, 0, negative 2.
By the way, we could have predicted early that the x and y coordinates were 0 by the fact that the z coordinate is 0, and curl always gives us something perpendicular. So we could, we could assume it's something that only has variables where their zeros are and doesn't have variables where.
Yeah. You guys with that? Basically, your vector field's flat, right? So where are the eddies going to be? Well, they're going to be flat too. And so the perpendicular direction of the eddies is going to be up or down. I don't know which. Apparently it's down. In other words, my eddies tend to be, wait, sorry, down, this one. Cool. Okay, so I found the curl. It's that. Good. How do I calculate a surface integral?
You need area. What would you?
Yeah, I need an area. So I need a parameterization of that thing, right?
See, it's a sphere, so,
It's a what now?
or a hemisphere.
It's a circular paraboloid. So.
Yeah, it's a circular paraboloid. It's not quite a sphere. So
Oh, okay.
why did I pick x and y to make my variable?
Because we are using x. Oh, yeah, because we are
Z
using.
equals the.
Yeah.
Yeah.
Yep.
Right.
Yeah.
Okay, so x comma y comma.
Oh my gosh. 4 minus x minus y. 4 minus x squared.
4 minus x squared minus y squared. Do not overthink this. You could parameterize this with r's and thetas.
It's disgusting pretty
It would be annoying, but you totally could. It would at least have the advantage of probably already having been converted to polar. You guys with me on that? Oh, actually, yeah, that would be a good idea. Should we do that?
Yes.
Should we pretend we noticed, or should we just move along with this graph thing? We'll pretend we noticed. So alternatively, how would we parameterize with r's and thetas?
Is it 2 cosine?
It's R. Oh, yeah.
Yeah. it's
Okay, so
R.
there's a radius, right,
Yeah.
Yep.
and a theta.
it's
So your out is the usual x, which is r cosine theta, and the usual y, which is r sine theta. And then what's special about your z here?
4 minus r squared.
That's 4 minus r squared. You guys cool with that?
Yep.
Okay, so either one of these parameterizations would work, right? It's just that if you do the x and y one, you're going to have to convert it to polar to integrate around the region that you're talking about. You guys see this? This is round. Okay, so what do? I need a. How about this? This is going to be a double integral now, right? And my curl is 0, 0, negative 2. And then I need to dot with, what should go here?
Yeah, let's go with the let's do the,
Oh, you plug it back in.
oh, it's the derivative of A, it's, right?
We all.
You guys forgot how to do surface integral.
Look,
Remember, this is a flux integral, right?
okay.
So to calculate a flux integral, I'm wondering how much of this stuff is flowing through the surface, right? So I need to dot with, yeah, except not your surface. Because it's not the surface you care about, it's whether it's flowing through it.
Oh,
So you need to dot with
S
a,
of R crossing S of
yeah, this
theta.
needs to be a normal factor, right? Which you get by crossing your two partials. And you need to figure out which order they go in,
Oh,
right?
It should just be
You guys remember that?
so are we going to be using X or Y or?
That.
So I'm going to use the r theta, right?
Okay.
So the r partial is going that way, and the theta partial is going
counterclockwise.
that way. And so I want
Theta?
r crossed with theta. So I want here, this guy needs to be SR crossed with S theta. This thing here, this first guy, that should be your vector field F of S, right? You guys all with me on that? But in this case, well, sorry, I used an F and I shouldn't have. That should be the curl of F evaluated at S. Right, but that's the same as just the curl of F because it doesn't depend on where you are. You guys all see that? Curl vector field's constant. Okay, how about, what are SR crossed with S theta?
First, we need to figure out what SR and S theta are.
Correct. Okay, so SR is cos theta, sine theta, comma, negative 2r. That's what I'm getting. Okay, how about S theta?
You got negative r sine theta?
Sometimes it's just because I'm thinking. Sometimes it's because I'm thinking about a part of the problem I did earlier that I'm worried I screwed up, or sometimes it's I'm thinking about something down the road, or sometimes it's that I overheard something, like the pauses don't mean anything.
R cosine theta and 0.
R cosine theta, comma 0. Okay, and actually I can do a lot better than calculating the whole thing. Why? No, easier.
Oh my gosh, we only have to
Because
calculate the
those two are
last
going to be
one.
0, so, right?
Yeah, we could ignore the X's.
So whatever, whatever, and the last one's the one that's going to matter,
So
right? So I need
r cosine squared minus no,
r
plus
cos squared plus r
sine squared.
sine squared, which is,
Wait, R cos squared, oh yeah, that's
which is
oh,
r,
that's just
right?
R, yeah.
Really?
Yeah, because the cosine squared plus sine squared.
It's a trigonometry.
Oh, okay.
That one and the half angle identical. Trig class should consist of those two things and not much else. It turns out that actually I need, when I taught trig, I thought that. And so I told the students that at the beginning, and then I realized that you actually need to know a bunch of shit that you can start doing that. It was kind of rough. So then what goes here? What goes here?
dr, oh yeah, r dr d theta, right?
Do we need that?
You don't need the r. Because
Oh.
you're doing a surface integral, right? So this cross product is the thing that's going to take care of that r for you.
Okay.
You guys see that?
So dr.
In fact, it's going to show up here anyway. But this should just be dr d theta. And then where do your r's go to cover this surface you're talking about over there?
0 to 2? Is that what you're saying?
Well,
0 to wherever that hits the XY plane, right?
Yep.
Which is at, don't overthink it, it's at 2.
Thank you.
Right, set that thing equal to 0 and solve.
Ah, damn it.
Get r is plus or minus 2. R is minus 2 doesn't make any sense, so you catch it. And then where do your thetas go?
0 to 2 pi.
0 to 2 pi. You guys with me on this? Okay, so all told we get the integral from 0 to 2 pi, the integral from 0 to 2 of minus 2 r d theta.
So,
Which is negative 4 pi integral from 0 to 2 of r dr, right? Which is half r squared evaluated from 0 to 2, which gives you
So negative 8 pi. That's a pretty, how do I say it?
The negative means it's going the opposite direction.
so the negative means that the vector field isn't helping you go around this thing. Probably because the vector field points the other friggin' direction.
But it's a pretty greedy function if it needs 8 pi's.
The 0, 0, negative 2, doesn't that just tell you that in the beginning? That it's not agreeing?
Yeah, so you could note that from the curl, right? The curl points down, right? And so the flux through this surface is going to be
the other direction.
negative. You guys see that?
Yep.
The surface orientation and the curl disagree.
Is that always a thing that we can look at?
Yeah.
The curl.
Yeah, as long as it's,
Sometimes it's not hard.
you know, if this has a bunch of x's, y's, and z's in it, you're probably not going to be able to eyeball the dot product of the curl and the normal vector to the surface. But sometimes you can. Like on this one, I can be like, yeah, I'm going to get a negative answer. When I get to that minus 8 pi, I'm like, yeah, at least it's got the right sign. Cool.
It's a pretty
Was this one easier with Stokes or not? Like, would this be easier to do with Stokes or to just directly calculate?
Stokes. I mean, we learned Stokes for a
Probably
reason.
about the same.
Oh yeah, no, Stokes was way overkill on this one. Let's calculate it the other way. So how do you calculate this the other way? You need the line integral, right?
Oh.
So here, I'll do it over here in this corner.
Okay, so R. Oh my gosh.
So you need the integral around C of f dotted with dr, right?
So what? R.
Okay, so f is that. So I'm going to integrate. I've got y minus x and 0. Yeah? And your curve is a radius 2 circle, right?
Yep.
And you need to go counterclockwise. So how do you do a line integral again? Like, okay, so f of t maybe
Oh.
is 2 cos t comma 2 sine t. Is that going the right direction? Yeah, I think so. It's counterclockwise, right? Oh, wait. This is the wrong category of thing. What did I screw up?
It's it needs to be two-dimensional. Or?
Yeah, this is in the xy plane, right? But this needs to be in the xy plane in 3 dimensions. So your z coordinate is 0.
That doesn't matter since you're dotting with the 0.
Yeah, it won't matter. I just want to make sure I can actually execute the dot product, right? Because if you have a 3 vector dotted with a 2, it just doesn't even make sense, right? So what else do you need here to calculate a line integral?
Partial.
You need r prime.
Yep.
So what's r prime here?
Negative 2 sine t. And then 2 cosine t. 0.
Cool. Okay, so
F of r of t.
so I need this dotted with r prime of t dt, right? And then I need a t. Where are the t's? There.
0 to 2, right?
Yeah, the beginning to the end, right? Okay, so they're from 0 to,
Oh, is it 2 pi?
it's 2 pi because they're an angle, right?
Okay.
And then here you need
F of r of t.
f of r of t, right?
So we
So
get
you
2 sine t and 2 cosine t.
2 sine t,
The negative 2 cosine t.
negative 2 sine t, comma,
Wait, shouldn't that be a negative 2 cosine t? The second one?
yeah,
Zero.
comma,
0.
0.
0 and 0.
And then dot product with,
Negative 2 sine t, 2 cosine t. 0. Oh my gosh. So yeah.
and then
So we
d,
get negative, yeah, we get negative 4 sine squared t minus 4 cosine squared t, which then the dt, so.
so you get the integral from 0 to 2 pi of negative 4 dt after a trig identity.
Yep.
And so you get,
Negative 8 pi.
dude, cool, love it. Which one was easier?
Left.
Oh.
Yeah, this thing, hella easier. So what's the moral of this example?
Don't always do the hardest, or don't always do.
Yes, Stokes is a big hammer, right?
Yeah.
Like, it takes some effort to swing that thing. Sometimes it's the right tool. Sometimes it's really, really overkill for pounding and finishing nails, right? Like, is it going to put a finishing nail in?
Yeah.
Oh, F yes. That thing's going to be done. But is it the best tool? Sometimes it's a lot of effort to get that thing and drag it down to the house and pound in picture nails with your sledgehammer. Right? So the other moral of the story is you're going to need to be able to calculate line integrals and surface integrals without thinking about it, right?
Okay.
Because if you're like, okay, so I convert this to a surface integral, and then how do you compute a surface integral again? Then things are bad, right?
Yeah.
Because you're not thinking Stokes, you're like stumbling over the bits and bobs in Stokes, and that'll be tough. Cool, cool?
Yep.
All right.